Today we're going to look at 7.2 Part 2. And remember, tomorrow is 7.3, and Thursday will be 7.4. So we're going to look at a little bit more with inverse trig. And what we're going to look at is a way to take something that has trig in it and get rid of the trig. Okay, kind of like convert something from trig to algebra. So trig has sines, cosines, and tangents in it. Algebra doesn't. So I'm going to show you how you can convert something from trig to algebra, at least in the kind of problems I give. Let me show you like an example. Here's an example of what we're going to do. We're going to take that and we're going to convert it to algebra. We're going to get rid of all the sines, the cosines, the tangents. Won't be any trig when we're done. And what you want to focus on is really two functions. I call this the outside. I call this one the inside. So the first step is to start with the inside trig function. And what we're going to do is we're going to draw it. So when you write down inverse cosine of v, that's a picture. You can imagine what that would look like. Inverse cosine is going to help us to set up a diagram, okay, a right triangle diagram. And the key is to remember when you do inverse trig, what are you always solving for? What is inverse trig used to figure out? Yeah?
Degrees or radians.
And that measures what? Yeah? The angle. So inverse trig is always used to find an angle. Okay, so keep that in mind. The way we're going to be able to draw it as a diagram is we're going to take that inner trig function that we're starting. We're going to start, I think it was inverse cosine, and we're going to rewrite it using the fact that inverse trig always gives you an angle, and we're going to rewrite it with regular trig. Once I do that, you should see how to make a diagram. Anytime you're given a trig function, whether it's sine, cosine, tangent, it doesn't matter which trig function, you basically know two sides of the triangle. So we're going to be able to label two sides of the triangle, and we're going to use Pythagorean theorem to figure out the third side. Okay, and we don't really need to worry about this last part. You can just focus on keeping in mind the Pythagorean theorem. All right, so it's kind of hard to just explain it and have it make 100% like sense. So we'll do a couple examples. All right, so this one says to write an algebraic formula, write an expression, to calculate the sine of the inverse cosine. As long as you have a regular trig function on the outside and an inverse trig function on the inside, you can always do this. You can get rid of all the trig in the problem. So, directions said, start with the inner trig function and rewrite it using regular trig. Okay. So the inner function, forget about sine for now. We'll come back to that at the end. Start with the inner function. That's inverse trig. What did we say that inverse trig is always used to find? Yeah? An angle. And how do we normally represent an angle when we don't know it? We usually use what kind of letter? Yeah? Yeah, we usually use a Greek letter. So I know that this, when you type inverse cosine and you plug in something, you're going to get an angle inside that red box. I don't know what angle is going to be inside that red box. I'm just going to call it theta. Now, it said to take that and rewrite it using regular trig. what could I do on both sides of this equation that would get rid of inverse cosine? Yeah?
You add cosine. You multiply both sides by cosine.
Something with cosine. But since cosine is a function, you cannot do arithmetic with a function. Arithmetic is add, subtract, multiply, divide. So we can take the cosine of each side. Yeah, I'm being picky about how you said it, but you were basically there. Take the cosine of what's on the left. Take the cosine of what's on the right. Cosine and inverse cosine will cancel each other out. And now, you have that. We'll see why I'm going to do this in a second, but how can you think of this left-hand side as a fraction? It's not a fraction, but I want to think of it as 1. Yeah? Yeah, think of it as v over 1. So this inside part tells us that the cosine is v over 1. What two sides are they giving me that I can now label in a triangle? Yeah?
You have the adjacent and the hypotenuse.
Right. This is the adjacent, v, and 1 is the hypotenuse. Adjacent is v, 1 is the hypotenuse. So what we've done now is we've taken what was in this red box and we turned it into a picture. So this picture is the red box. Any question on the picture? Now we have to go back and look at what do they want to know about this picture. They want the sign of the picture that we just drew. They want the sign of the picture. Well, what's the definition of sign?
Opposite over hypotenuse.
Opposite over hypotenuse. Do we know the opposite?
No.
No, so we need to find it. We can temporarily call it x. But how can we actually find what it is in terms of these other two sides? Yeah? Yeah, use the Pythagorean theorem. So x squared plus v squared equals 1 squared. And now solve for x. And that's what we're going to label this side as. So what is x? Yeah?
It's going to be the square root of 1 minus v. Or v squared.
V squared.
It needs to be squared still under the square root.
Yes.
Because
So that side is 1 minus v squared. Square root of 1 minus v squared. Now we know all the sides. Okay? They want the sign. So the sign is opposite over hypotenuse. So the square root of 1 minus v squared over 1. Since it's over 1, we don't need to put over 1. Okay. Now let's try it. Let's type this in y1. Let's put that in y2. And let's see if they look the same. If they do, then we found a formula that got rid of all the trig, and it's just algebra, and it should give us exactly the same answers. Okay, let's try it. So let's do the sine of the inverse cosine of x, and then put the square root of 1 minus x squared. All right, let's do zoom 7. 11 degrees. Let me switch to radians. Okay, make sure you are in radians. Okay, there's the original. And I don't know if you saw it, that was the new one. Did they trace right on top of each other? Yeah, I mean, then they're the same thing. It doesn't prove they're the same thing, but I mean, we did it algebraically, so we know they're the same thing. The other thing you can do is go to your table. And you could just try different values. Now remember, you couldn't plug in a value like 3 here, because 3 squared is 9, 1 minus 9 is negative 8. You can't take the square root of negative 8. So you have to make sure v doesn't go above 1, and v doesn't go below 1. Yeah?
0.3?
No, you could plug in 0, that'd be okay. 1 minus 0 is 0, and the square, 1 minus 0 is 1, and the square root of 1 is 1. So you could plug in 0. But what's the lowest number you could plug in and not have a negative under the square root? Yeah, negative 1. It's exactly the domain of inverse cosine, negative 1 to 1. And they should have exactly the same domains and ranges. So try like 0.6. Yep. Each formula gave us the same result. 0.7. Yep. Same result. Negative 0.8. Yep. Same result. If you try to go above 1, you're going to get an error. That's outside the domain. Okay. And if you go below negative 1, that's also outside the domain. And so I'm just checking by graphing it and looking at the table to make sure what I found is right and it looks good. Yeah.
Is that by like coincidence or is that like actually what's happening?
Is what a coincidence?
Like the domain you were saying, like of cosine is just
No, they have to be the same because they're equal to each other. If two functions are exactly equal, then they have to have the same domains and ranges. I'm trying to think if there's ever really an exception to that. I'd have to think more, but in our case, they have to be the same.
Okay.
Any other questions on that? Sweet. Let's try another one where they give us a formula with trig, and when we're done, we don't want to have any trig. You can have squares, adding, subtracting, square roots, multiplying, dividing. You can have any of that, but you can't have tangent and inverse sine. Okay, so what do we start with here? The one on the outside or the one on the inside?
Inside.
Inside. And the inside one is what kind of trig? Yeah.
Inverse sine.
It's inverse trig, specifically inverse sine. So we know when you do inverse trig, you're going to get an answer that's what? When you're solving for an angle. Okay, you're always solving for an angle. So I don't know what angle this is going to be, but I know that the inverse sine is going to come out to an angle. So let's use theta as our Greek letter that it comes out to. Rewriting it so inverse sine is gone. What would be my new equation? Yeah? V is equal to the sine of theta. And now that you know the sine is V, you should be able to draw a diagram that represents this part of the problem. Okay, you're going to draw a diagram for your angle. It doesn't matter where you put the angle. It just has to be one of the acute angles. Top, bottom, you can draw your triangle this way if you want. It doesn't matter how you do it. Okay, so they're telling us that the sine is equal to V. So that means what two sides have they given us? Yep. Opposite and hypotenuse. So you need to put something here and something here so that when you do the opposite divided by the hypotenuse, it comes out to V. So what could you put in each of those spots? Yeah?
V and 1.
Yeah. V and 1. That's the simplest way to do it. I guess you could do 2V and 2. But it's more complicated. So we'll just stick to V and 1. Okay. Any question on the diagram? Now we have to use that diagram to find the tangent. Okay. What's the definition for tangent? Yeah. So it's opposite over adjacent. Okay, well, I don't know the adjacent. So what could I call the adjacent side for now?
A.
Yeah, you call it A or X. Call it just a letter. I would use an English letter for a side. And what equation could I set up with those three sides now? Yeah.
Pythagorean theorem.
Yeah, and what would that be with those values?
Oh, a squared plus v squared equals 1 squared.
A squared plus v squared equals what?
1 squared.
1 squared. Okay, so we've got a squared plus v squared equals 1. And we're solving for a. I want to solve for a so I can do this.
So you subtract the v squared to the other side.
Subtract the v squared to the other side and
Oh, square root.
square root. So that's a. 1 minus v, square root of 1 minus v squared. Now I got all three sides, I can find anything they want. Okay, they want the tangent. Okay, so opposite over adjacent. Okay, so what's the opposite? Yeah, v. Over. And what's the adjacent? Yeah.
Square root of 1 minus v2, v squared.
Square root of 1 minus v squared. Now, algebraically, that is equivalent. If you put that in y1 and you put that in y2, they should look the same. But, what's wrong with this as a final answer? Something we don't like to generally do, yeah? Yeah, so we just don't want to leave the square root in the bottom. So what would you multiply the top and the bottom by?
The square root of 1 minus v squared.
Yeah, multiply the top and the bottom by the square root of 1 minus v squared. Okay, and I'm not going to do it this time, but you could put what's on the left in y1, put the right in y2, go to your table, try some different values, and they will come out the same. So this is an algebraic formula that gives you exactly the same result as this trig formula. Just no trig, trig. Any question on that? Okay. This is kind of the same thing. Did anyone want to see one more of the type where you've got a regular on the outside and an inverse on the inside? Okay, it'd be pretty similar to examples 1 and 2. All right, so then let's try this one. This one's a little different. So this doesn't say to come up with a formula. It says to evaluate it. Evaluate means when you're done, you want an answer. Usually it's numeric. Okay, so we're going to evaluate this without a calculator, which means that special things have to happen. Okay, it can't come out to some weird decimal. We wouldn't be able to do it in our head. So this has to be something that we can do easily somehow. So what I would do is follow order of operations. Figure out what the inside is first. Okay? Once you figure that out, then you're going to take the inverse sign of whatever you get. Okay, but forget about inverse sign for now. What is 3 pi over 4 in degrees?
135.
It's 135. 135 degrees is a multiple of what number?
45.
Yes, that is a multiple of 45. And when an angle is a multiple of 45, and I mentioned this in the homework, what can you use to figure it out if you don't have it memorized? You can use what?
Pythagorean theorem with like the one.
Not for angles. That's only for sides. Yep.
Unit circle?
Use the unit circle. Yep. So 135 degrees. Let's think about where that would be on the unit circle. Here's 90. Here's 180. Where's 135? Yep.
In between them?
Yep.
Halfway?
It's exactly halfway between them. What is the coordinate for 135 degrees on the unit circle? Keep in mind, you just need to know the lengths of these two sides. But remember, the first one is a negative. Yep.
Isn't it negative square root of 2 over 2?
Mm-hmm.
And then square root of 2 over 2.
Square root of 2 over 2. And the formula for tangent. Does anybody remember this is x and this is y? What's the formula for tangent?
Y over X.
Y over x. Yep. That's y, and that's x. What do you get if you divide y by x here?
Negative 1.
Negative 1. Okay, so now we know the inside. The tangent of 3 pi over 4 is negative 1. Okay, so we got that. Now we need the inverse sine of negative 1. Inverse sine of negative 1. Well, what are we solving for? Because we're doing inverse trig. So we're trying to find what?
Angle.
Trying to find an angle. So another way to think of this is the sine of what angle gives you an answer of negative 1. What number could you fill in for the question mark? That's the answer to the problem. The easiest way I think to think about it without a calculator is draw it. Draw your graph of sine. Here are your quarter points. Where does the graph of sine hit negative 1? That's, if you know where it hits negative 1, you just have to tell me what the angle would be on the x-axis. Yep.
Negative, it would hit negative 1 at pi. Yeah, pi.
It hits 0. That's where it hits 0. So at pi, it hits 0.
3 pi halves.
Yes, 3 pi over 2. That is where you hit negative 1 in the first cycle. Now, if that didn't come out to negative 1, positive 1, or 0, we would have never been able to figure it out. If it came out to like 0.6, I mean, how are you going to figure out where you hit 0.6? That's hard to figure out. It had to come out to 1, negative 1, or 0 to make it doable. Okay, so what angle is it? 3 pi over 2. And that's the answer to the question. All right, so any question on the process we went through to figure that out? So it's starting to tie together lots of things here.
What are the other coordinates for like the ones that are, if it was like closer to 90 or if it was closer to 180?
So those have a root 3 over 2 and a 1/2 in them. It depends which one. If you're doing like this one, that's 1/2 root 3 over 2. That would be the coordinate for 60. And the coordinate for 30 would be flipped. Root 3 over 2, 1/2. And then you can mirror image that into any quadrant. And then one of them or both of them just become a negative. So yeah, don't forget about the unit circle. That's still pretty important. Okay, but the 30s and the 60s were not needed in this problem. Okay, just the 45. Yep.
Could you explain how you changed inverse sine of negative 1 sine of sine of something equals negative 1?
So I know that when I do the inverse sine of negative 1, it's inverse trig, so I know I'm going to get an angle. right? Now take the sine of both sides. That cancels. So now the sine of something equals -1. Any other questions on? Yep.
If it weren't -1, would it just not be possible without a calculator, or would it just get more difficult?
Well, as long as it's -1, 1, or 0, we could do those pretty easy because they land at the quarter points. But if it's a number other than that, you can do it without a calculator, but we have to start using methods to approximate it, and it's not really something we've studied. So yes, it is definitely doable without a calculator, but I would make sure it comes out to one of the ones I just mentioned. Yeah. All right, let's try this one. Now, again, it's the same directions. They want us to evaluate without a calculator. You're never going to be able to figure out what inverse tangent of a half is. That is not a nice number. But you don't need to figure out the inverse tangent of a half. They're asking for the cosine of the inverse tangent. That I can figure out. So I can figure out this whole thing. I just can't figure out this part. So let's go through it and see what happens. What trig function do we usually start with? Like, I guess, which position? The outer or the inner? Which one? Yeah, the inner. So let's start with the inner. And it's inverse trig. The last problem was regular trig. Okay, that was a different question. This is more similar to what we did in the first two problems. It has inverse trig on the inside. The difference is it's all numbers instead of having inverse trig on the inside with a letter. So this one's actually going to be easier than the first two. Okay. When I do inverse tangent, what kind of answer am I going to get? I'm going to get an angle. I don't know what that angle is. So what should I call it?
Theta.
Okay, let's call it theta. Now let's rewrite this using regular trig. What would this equation look like if you get rid of the inverse tangent and rewrite it in terms of tangent? Yeah?
Tangent theta equals 1, right?
Right, you're going to get the tangent of theta equals a half if you take the tangent of both sides. Now, draw that as a picture, but you don't have to worry about any letters. The opposite is 1, and the adjacent is 2. Opposite, adjacent. So what's my hypotenuse going to be? Yeah.
1 plus 2 squared.
So what's your final answer going to be?
Square root of 5.
Yep. Okay. So now you've got a triangle with all your sides labeled, and they want to know the cosine. What is the cosine of that diagonal? Yeah. It's 2 over the square root of 5, which is 2 root 5 over 5. And that's an easy one. We can check pretty quick. Let's take the cosine of the inverse tangent of 0.5. Make sure you are in radians. And now take 2 square root 5 over 5. 2 square root 5 divided by 5. Exactly the same thing. So any question on how we evaluated that expression and got the exact answer? Okay. This is another one that's pretty similar to the last one. You got regular trig on the outside, you got inverse on the inside, and you have the number 1/2. In fact, it's almost the same problem, except I changed inverse tangent to inverse sine. Anyone want me to go through how to do that one? You can do it the same way as this one. Draw your picture, do Pythagorean theorem, except instead of the opposite being 1 and the adjacent being 2, the opposite is going to be 1 and the hypotenuse is going to be what?
2.
2. Because sine is opposite over hypotenuse. Yep. It's a little different, but pretty similar. All right, so just a reminder, we're going to finish up by solving an equation like that. If you can find one solution to a trig equation, that means there's infinitely many. In general, how often does an answer repeat when you have a trig function?
Infinite number of times, like, because I'm
Well,
saying
that's,
like
hold on a second. That's how many times it repeats. But how often does it repeat?
once every rotation or revolution or
Every period, yes. So it's got to repeat once every cycle, once every period. Okay. All right. So let's try this one. Sine of x equals 0.6. Okay. And I'm going to tie in something we did before and see if we remember something we did earlier. Okay. How are you going to get x by itself here and get rid of the sign? Yeah. Take the inverse sine of both sides. Inverse sine cancels regular sine. And we get x is about, okay, let's do it in degrees. And now I'm going to type in inverse sine of 0.6. Inverse sine 0.6. But I said degrees. So let's do it in degrees. Okay, you get about 36.87 degrees. Now, if you write that, you've only given me one solution. What do I put on the end of this to indicate that it repeats forever? And this is sine. So remember what the period of sine is, yeah?
Well, was it 2 pi? You write like plus 2 pi.
Yep. Remember where n is an integer. So you can add and subtract 2 pi to that. Well, careful. That would be in radians. So what should I actually put here? Because I'm doing it in degrees.
Oh, 360.
360, yeah. So you can add or subtract 360 as many times as you want to that number, and you'll get an answer in an earlier or later cycle. But we're not done. Think about what sine looks like. That's the graph of sine. And we're asking where it equals 0.6. Well, the highest it goes is 1, so it's a little more than halfway up. How many answers do you get per cycle?
2.
2. This 36.87, that's that one. You still need that one. Anybody remember how we get that other answer?
Can't you just do the second calculator cycle on the graphing calculator?
If we were doing it graphing, we could, but we got to start to learn how to do it algebraically because of stuff that's going to come up. So this ties in with something we did earlier. So if you don't quite remember, that would make sense. Yeah?
Is it something like when you add like 180 or minus 1? I forget which one it is with something with the 180.
Yep, it has something to do with the 180. we need to figure out what quadrant that second answer is in. Anybody remember the diagram we had?
So
Yep.
it was like all of them the first.
Yeah.
Then I think subtraction. No, never mind. I don't know the other thing.
Anybody remember that chart? The letters that go in the boxes? Yeah.
SATA. SAAS and then TT.
And what goes in this box?
I thought that was an S.
Yep. And the one below it?
T.
And then the last one is the C.
Yeah.
So this is where all the trig functions are positive, just the sine.
Tangent.
Now, what function are we working with?
Sine.
We're working with sine, and we want to know where sine is equal to what kind of number is 0.6.
Positive.
That's a positive number. 36, well, let's figure this out first. What two quadrants is sine positive?
1, 2.
Yes, sine is positive in quadrants 1 and 2. 36.87 is in which quadrant? That's in quadrant 1. So we already have the quadrant 1 answer. So now we know where the second answer is. It's quadrant 2. That's a reference angle. Does anybody remember what the formula is to find the answer in quadrant 2? Yeah?
We have to subtract that number that we have there from 180.
Yes.
And then that's going to be the reference angle for the second one.
So that's going to be our other answer. So yeah, 180 minus, I still have the last answer on the screen. So I can just do 180 minus what I had before. And the other answer is 143.13. Now, how often, or what do we put on the end of that one to indicate that repeats?
360.
Yep. And the nice part is you can double check that by graphing it. Put one side in y1, one side in y2, and you could do the intersect and make sure those are right. But we have to know how to do it algebraically because of stuff that's going to be coming up. Any question on that? And you could do the same thing in degrees, right? Except instead of putting like a plus 360, you do a plus 2 pi. Okay. In fact, I'll do the next one in radians just to practice. The last slide? So this, I was going to mention this last thing. Some trig functions we don't have a button for. So the problem that we're going to do next, I think it said cotangent. Yes. We got to think about how to work with that. We don't have an inverse cotangent button.
Wouldn't it just be 1 over negative of tangent negative 1?
If you flip the whole inverse tangent, it doesn't give you inverse cotangent.
Are the relationships the same for like the inverses? Like, so regularly sine over, I mean, yeah, cotangent equals 1 over tangent.
Yes,
So
cotangent is 1 over tangent, but inverse cotangent is not 1 over inverse tangent.
Would be
Doesn't work that way.
would be negative 1 over inverse tangent.
Well, let's see what happens here.
Oh.
So, ideally, if we had inverse cotangent, we would do that on both sides to get x by itself. We don't have it. So, I know the cotangent is 2.5. What's the trig function we know that's connected to cotangent? Yeah? Nope, sine is connected with cosecant.
Oh, tangent.
Tangent, yes. So if the cotangent is 2.5, what's the tangent? Yeah? 1 over 2.5. Now we should be able to get x by itself. What what do we do on both sides to get rid of tangent now? And we can do this because we have a button for it. Yeah?
To the inverse tangent.
Take the inverse tangent. Again, if you had inverse cotangent, you could have done that right away, but we don't. So we had to rewrite it using a reciprocal identity. Okay, so take the inverse tangent on the left. Take the inverse tangent of what's on the right. And I said I would do this one in radians. Okay, so I'll do it in radians. Okay, so switch to radians. Inverse tangent of 1 divided by 2.5 gives me 0.38 radians. Bless you. Now, what do I put on the end of that to indicate it repeats forever? And remember, two things. You're dealing with tangent, and you're in radians. Yeah?
Would it still be with the 180 n and the 360 n?
Nope. So we got to remember two things. We're in tangent, we're using tangent, and we're in radians now. Yep. Pi n. Yes. Because the cycle of tangent is pi. And we're in radians. If you said 180, you could do that if you were in degrees. Now, tangent looks like this. I think something kind of like that. And we've got a horizontal line at 1 divided by 2.5. So, some number. How many answers do you get per cycle for tangent?
1.
Just one. Yep. Just one. So you don't have to worry about 2 in this case. If there was a second answer, I'd do the same thing again. I'd say, all right, tangent is positive in which 2 quadrants? This one and this one. And then I'd say, okay, I've got my reference angle. It's 0.38. How do I get the other answer? Well, in this quadrant, that's pi plus your reference angle, or 180 plus your reference angle. But I don't need to do that. Okay. Any questions on that? All right. So that pretty much finishes up 7-2. So there's not that many because we did most of it yesterday. So it's 37, 38, 41, 42, and 44 to 53. Okay, so we'll go over that first thing tomorrow, and then we'll do 7-3 and 7-4 on Thursday.